Okay, so now we move on to the block diagram of an optical communication system. So we have the source of information, which could be signals from a television or a cell phone or a computer or a regular landline phone. I mean, this is not the limit. I mean, you could have any source of information. You need to do some amount of signal processing. The signal processing is just a black box that I'm talking about. Signal could be in analog. It needs to be converted into digital. As I said, predominantly optical communication happens in the digital domain. You may need to do some kind of shaping in the time domain. You may need to do some kind of processing. You may need to do coding. Right? All that is included in this box. All that can be fed multiplexed or individually fed into the optical transmitter. But in general, we say that the source of information now needs to get converted from the electrical domain to the optical domain. So there is a electrical to optical conversion that is happening. So the red is kind of indicative that the signal is in the electrical domain. Blue is indicative that the signal is in the optical domain. Now, electrical to optical conversion is essentially a transducer which converts electrical signal to an optical signal without generating its own distortion. Okay? And typically the transducers used are either LEDs or laser diodes. And you could use direct modulation or you could use external modulation. Direct modulation would mean that you're turning the LED on and off by changing its current high and low. But if you want to introduce a phase, that may not work. So you need to, in that case, you need to take an LED or laser diode or an LED and take it through an external device, which is a modulator, which could do, so the input to the modulator is, on one side is light and the other side the electrical signal. And out comes modulated light. So depending on the kind of modulation you want to do, you would choose the design of the modulator appropriately. We will talk about in detail of how to do phase modulation later. But in any case, the transmitter converts your electrical signal to optical signal. Then there could be a coupler, there could be a switch, there could be a router, depending on the kind of network that you are using. There could be a filter. Because if you are multiplexing all this in different carrier frequencies, this could be in FC1, this could be in FC2, then maybe you need a filter to route some of the signals to some part of the network and so on. So there could be some passive devices there. There could be. There need not be also. Then it passes through your optical fiber. The attenuation in an optical fiber, as I said, the best attenuation is roughly 0.2 dB per kilometer for a commercial standard single mode fiber, a standard single mode fiber. We'll talk about what is a standard single mode fiber when we talk about channel, but this is the most commonly used fiber in a communication link, and that comes with an attenuation of 0.2 dB per kilometer, which means that after a distance of, let's say, 100 kilometer, there's a loss of 20 dB, which means the power gets lost 100 times. The power reduces by 100 times. And so if you want to transmit for longer distances, you need to boost up the power somewhere in the middle, and that is done by an optical amplifier. An optical amplifier will amplify optical power without converting it into an electrical domain. It could go through other lengths of fiber depending on the link that you have. You could have multiple spans, you could have only a single span, you could have a point-to-point network without an amplifier, and so on. Then again at the receiver end there could be a coupler, switch, filter, router, etc. depending on what network you are building. And then you have a receiver which is basically a optical to electrical converter. And so that optical to electrical transducers typically are photodiodes. a photodiode which will sense light and give you a current. But again, to determine phase, a simple photodiode is not sufficient, because a photodiode is sensitive to only the intensity of light. It is not sensitive to the phase of light. So you need to have some modification in the receiver to detect phase, which we will talk about in detail when we do receivers. The amplifiers, as I said, the most commonly used amplifier is a dope fiber amplifier. You could also use semiconductor amplifiers. People also use what are called as Raman amplifiers. So that again will come in our module where we are talking about amplifiers. And after the optical to electrical conversion is done, you could do the demultiplexing as you did earlier, and you could be sending the information to the recipient. So the whole course is now about this diagram now. We need to learn more about the transmitters, more about the fiber, more about the amplifiers, more about these components, more about the receivers, and how to set up this link. I mean, this need not be kind of point-to-point link. There could be different architectures where the network is set up. So we'll keep referring to this diagram again and again, see what part are we doing in each week. So today's is going to be about transmitters. Okay. Before we go ahead, some basic units you may be aware of, but then just to remind you, typically power, whenever there is a change over orders of magnitude, we represent the quantity in logarithmic units. So power in dBm is 10 log to the base 10 power in milliwatt. So what would be 0 dBm? What would be minus 30 dBm? 10 power minus 3 in milliwatt, which is 1 microwatt. What would be plus 30 dBm? So you should be familiar with these units. Again, loss is designated again as a logarithmic unit, minus 10 log P out by P in. So the other again fundamental information that which may be useful to you is that intensity is number of photons times the energy per photon. Power per area is intensity. So energy per time is power. Power per area is intensity. Let's say there is the intensity in the screen is certain milliwatts per centimeter square. It means that the power falling on the screen per unit area is that. And intensity by itself is number of photons multiplied by energy of one photon. And energy of one photon, we know it is h times frequency of the photon, or this is hc by lambda. Lambda is a wavelength of light. So the question to you is this. An optical transmitter, wavelength is 0.8 micron. It's a typical wavelength of optical communication. It's operating at 1 gigabits per second. In non-return to zero, on-off keyed modulation. By now you should know what is on-off key, you should know what is non-return to zero. The transmitter is launching 3 dBm of average power. The total fiber loss is 6 dB. What is the received number of photons after that length of fiber in 1 bit? You can assume that there are equal number of zeros and ones. So I know that the launched average power is P at the input is 3 dBm. At the transmitter, there is a fiber and then there is a receiver. This is 3 dBm. Okay. I do not know the length of the fiber here, but I know that the total fiber loss is 6 dB. So what power do I get at the receiver? Minus 3 dBm. This is the benefit of doing everything in the log scale. So in log scale, division in the linear scale becomes subtraction. Now the receiver has minus 3 dBm of average power. The question is, we want to find out the number of photons in 1 bit. When I say 1 bit, it actually means bit 1. So there could be a bit 1 and a bit 0, right? So you could have a bit 1 and a bit 0. You want to find out how many photons are there in this bit. Remember, this is average power. Now, to find the number of photons, this power, if I know the power is P1, the peak power is P1, multiplied by my bit slot is going to give me energy. And once I know energy, I can calculate number of photons. Alright, so to find out energy, energy is equal to P1 times PV. But I don't know the P1, I don't know the peak power, I know only the average power. But I already gave you an information that in a typical communication system, the number of zeros and the number of ones are randomly distributed, and so they are equal. And so if you have equal number of zeros and equal number of ones, half the time, let's say you have a total duration of time, half the time it is 1 and half the time it is 0. So what would be the relation between average power and peak power? This P1 should be equal to twice P average. So you know what your P1 is because you know what is the average power received here. And you know what the bit slot is. That gives you the energy. And once I know the energy, I know the number of photons because n times number of photons times h nu or hc by lambda is total energy. So I can find out the number of photons. Of course, you have to remember that this P1 now needs to get substituted in linear units because you are multiplying power with time. So now what is minus 3 dBm? 0 dBm is 1 milliwatt. Minus 3 dBm would be 50% of that. So this would be 0.5 milliwatt or this would be 500 microwatt. C, of course, is the speed of light. So I would say P1, which is twice P average, so twice 500 microwatt. So that will be again 1 milliwatt. 1 milliwatt times bit slot, bit duration. Now what is bit duration here? It is 1 Gbps, so the bit slot will be 1 over 1 Gbps, 1 nanosecond. So I know this is 1 nanosecond, from that I can find out what my number of photons is. Alright, so you can do that numerical calculation later, but this is how you go about approaching, finding out the number. These number of photon calculation, etc. becomes important later when we talk about receiver sensitivity and so on. Okay.